welcome to this explainer. Today, we're diving into what I like to call the starting line mystery. We're going to solve a puzzle that's literally hiding in plain sight at your local athletics track, and, we might just unlock the secrets of pi and perimeters along the way. Let's get right into it. So, imagine you're sitting at the Olympics, right? You're watching athletes line up for 4x100-meter relay. And you've probably noticed this before. The runners in the outer lanes are placed way ahead of the runners on the inside. It's the super visually striking, almost kind of unbalanced formation, isn't it? I mean, the person in lane 8 is starting way up ahead, while the poor person in lane 1 is stuck all the way at the very back of the pack. Now, this creates an immediate mystery for us to solve. Since the finish line is exactly the same for every single person on that track, does this massive stagger give those outer runners an unfair advantage? Or are the inner runners somehow at a disadvantage? Think about it. If the race is precisely 400 meters for everyone, how on earth do the organizers figure out exactly where each runner needs to stand so nobody gets cheated? Well, to figure this out, we need to understand that this stagger isn't just a wild guess. It's an absolutely perfectly calculated mathematical necessity.
Okay, so to solve this track puzzle, we actually have to take a quick step back to basic geometry. Don't worry, it's pretty cool. Take a simple square. No matter how huge or how tiny you draw it, the ratio of its perimeter to its side is always exactly 4:1. It scales perfectly every single time. Well, it turns out circles possess a very similar kind of magic. Regardless of their size, circles have this permanent, unchanging ratio of their own. And this is what we call the C/D ratio.
Ancient mathematicians discovered something absolutely incredible about this. No matter how massive a circle is, we're talking like the equator of an entire planet, or how tiny it is, like the face of a little coin in your pocket, the ratio of its circumference to its diameter literally never changes. It is an absolute constant. This C/D ratio acts as this profound mathematical bridge, connecting the straight-edged, predictable world of polygons with the infinite, sweeping curves of nature. And you guessed it, it's the exact key to solving our running track mystery. And what's really wild is that you can actually prove this ratio yourself, at home, right now. All you need is just a standard cotton reel and some thin thread. So, first, measure the diameter of the reel. Then, tightly wrap that thread around it exactly 20 times. Once you've done that, unwrap the thread, measure its total length, and just divide that length by 20 times your original diameter. If you punch that into a calculator, you're gonna find your result lands right between 3.1 and 3.2. Congratulations, you've just experimentally discovered pi. Now, of course, professional mathematicians weren't just satisfied with a rough thread measurement, right? This ratio actually sparked this epic global quest that spanned literally thousands of years. Way back in 1900 BCE, Mesopotamians estimated it at around 3.125. Then, by 250 BCE, Archimedes cleverly tracked the value using polygons. Jumping over to China in 480 CE, Zhu Chongzhi calculated this wildly accurate fraction. And then finally, in the 15th century, a complete tectonic shift occurred in India with a mathematician named Madhava. But actually, real quick, before we get to Madhava, we really have to recognize the profound insight of the great Indian mathematician Aryabhata. This was back in 499 CE. When calculating his value of pi, which was highly accurate, by the way, at 3.1416, he specifically described it using the Sanskrit word asana, and that translates to approaching or approximate. See, Aryabhata intuitively understood that the C/D ratio was kind of this slippery concept, right? One that could just never be perfectly written out as one simple finished fraction. So then we get to Madhava of Sangamagrama, and he completely changed the game. He realized that pi wasn't just some geometric shape to be cut up. It was actually a limit to be reached. By summing fractions in an alternating infinite series, the guy effectively birthed calculus. No big deal, right? This brand new analytical approach allowed him to calculate pi to an astonishing 11 decimal places. It absolutely revolutionized how we understand curves. Honestly, the best way to think about its digits is like a giant train, just carrying numbers endlessly down the tracks. Unlike simple fractions that eventually repeat their decimals, like how 1/3 just becomes 0.333 forever, pi has absolutely zero repeating rhythmic pattern. None. The numbers 3.14159.265. They just keep rolling on forever and ever into infinity without ever settling into a loop. And because those digits never end and never ever repeat, pi is mathematically classified as an irrational number. Basically, this means it is literally impossible to write it out as a perfect ratio of two whole integers.
So, you know how we often use fractions like 22/7 in school? Well, while those are fantastic, close enough approximations for everyday practical use, they are never perfectly exactly equal to pi. Since pi doesn't repeat, memorizing the digits can obviously be a bit tricky. But hey, if you ever need to remember the first few decimal places to, say, impress your friends at a party or just pass a math test, just memorize this one simple sentence: How I wish I could recollect pi. Seriously, if you count the number of letters in each word, so how is 3, I is 1, wish is 4, I is 1, could is 5, recollect is 9, and pi is 2, you instantly get 3.141592. Pretty cool, right?
All right, so let's take all this really fascinating knowledge about pi and bring it back down to Earth to solve our track problem. We know the distance around a whole circle, its circumference, is 2 times pi times the radius. So basic logic tells us that a semicircle, which is obviously just exactly half of that shape, must have an arc length that is exactly half the formula. In other words, the distance around a semicircle is simply pi times the radius. That's it.
And let's see how this builds our solution. Here we are, back at our original mystery, a standard 400-meter athletics track. If you really look closely at the shape, you'll realize the athletic track isn't actually an oval at all. It's really just 2 straight, parallel lines capped off by 2 perfect semicircles on the ends. And guess what? We now have the exact mathematical tools we need to measure this whole shebang.
So let's run the numbers for the runner in that innermost lane. Step 1, they run 2 straight sections. Those are 84.39 meters each, which totals 168.78 meters. Okay, step 2, they run 2 semicircles, and together those make 1 full circle. Using our brand new pi formula, 2 times pi times their specific radius of 36.8 meters gives us 231.22 meters. Finally, step 3, we just add those straightaways and the curves together and boom, you hit exactly 400 meters. Perfect. But here is the absolute crucial point. While those straightaways are identical in length for absolutely everyone on the track, the runners in the outer lanes are running on semicircles with a progressively larger radius. And because radius directly multiplies by pi to create distance, a larger radius undeniably creates a longer run. There's no getting around it. Therefore, that massive stagger isn't just some weird quirk. It is a strict, unbreakable mathematical requirement. It's the only way to ensure every single person runs exactly 400 meters, making the race perfectly 100% fair. Well, to wrap up this explainer, I want to leave you with this final kind of mind-bending geometric paradox to calculate on your own. Based on everything we just talked about with pi, radius, and arc lengths, imagine you have point A and point B. If you have one path connecting them made of a single giant semicircle, and another path made of 3 smaller consecutive semicircles connecting those exact same 2 points, which path is actually longer? Seriously, think about the radius formula, maybe even try mapping it out on some paper. You might be absolutely floored by the answer. Anyway, thanks so much for joining me on this mathematical journey today. Catch you next time.